I've just been.
I put it for this. Gadget might actually don't want to look at your environment or the thing around you.
They do everything.
I don't even know it. It's really from OC.
Every single one I made have a very simple, direct, reliable solution.
Yeah, that's what I just said.
Just like
There is one way I would have
go off into left field anyway.
Yeah.
Yeah, without finding out the answer, you can never find it.
Yes.
How much would you wait, what is
That's what I plan on taking for the dream.
Wait, I wonder.
It's the yeah, I already have 4 p.m.
Oh, wait. You say that.
Are you gonna take it?
If I'm here.
Oh yeah, we're.
I might be abroad, right? That's how you.
Oh, yeah.
I might be in Japan.
It's not.
You know the issue. Yeah, I know.
It's probably
I heard about that.
This is
They're not gonna bug about that. The facility. I heard.
Which is one efficient because this is more.
My issue is that I want to take it's like my dad is my social class and then 560 is I've gotta take that class because I can't.
Everything I've heard is education.
It's not commission. Yeah.
Monday, Wednesday.
560 is I know it. I mean, it's generally just.
I could. I don't.
I know. Wait, am I actually?
So assuming I'm correct.
This is. All the
Maybe I just audit it. You could audit it. You could take 560 when you schedule. I think part is here. So, if you want my opinion, I think you should audit 365 if you don't want it, and take 560. Well, if you have a portfolio, that's right now, 560, I would say you can really calculate this. I was like, how much
I've never done any front end or back end. Wait, what do you mean by no
There's a crack in my phone where
I don't know.
there's a crack in my phone. I'm not even joking. That's exactly what happened.
Wait, actually, I did filter. I actually did anything I went food shopping over the weekend and I got 2 things. Because I don't need anything because I have Tupperware of my mom's cooking. So I went to the grocery store and I got 2 things.
Because
One was a
punch the
bus.
screen in a YouTube short.
The other, my greatest purchase yet.
I don't know if I'd be right next to the mic too. That's been recorded.
I was watching it.
That's been recorded. Yeah.
Every so often I will text all of my roommates and I will be like, I'm picking up the dino nuggets. They will get to be saying like, greedy and then 1 second. I need to get more I want my dinosaurs. I didn't say don't touch them.
Excellent.
So like no one.
Who looked at the homework?
Did we say everyone?
Yeah, everyone raised their hands. So you are, no, I didn't, no, not right now. Everybody raised their hand last time when I said who's gonna look at the homework today, and you did not. So, yeah. Today we're gonna go through ASLR, which is the next mitigation on our list. I am not going to give you guys ASLR challenges and homeworks in this class. The reason that I'm going to not do that, we will get into pretty deeply in this lecture today. The short answer is you are generally relying on program complexity to beat ASLR. And so any homework that I gave you that provided the necessary complexity would either give away the answer immediately, in which case it's not worth you going through it, or would be so long that you would not have the ability to finish the homework. Right? It would also mean that I either have to use real programs that would be fairly complicated for you to understand in a 2-week period, or I would have to contrive an extremely complicated program in a short period of time to hand to you that you would also then have to figure out. Right? There are kind of two choices that I had looking at the second half of this class, which is what we are in now. One is focus strongly on beating ASLR, and the other was go kind of in-depth into heaps. And a lot of people were more interested in looking at heaps, and so I would kind of prefer to use the second half of class to do that. When we talk about heaps, I'm going to go through a couple paradigms in heap development. What a lot of people do who are trying to learn to own heaps, who aren't looking at real-world examples, they will kind of rabbit hole down the type of work that is shown in Mallet Maleficarum, which is attacking the heap allocator itself. In my view, that is a mistake. So I will walk you through some pieces of that in the next lab so that you can kind of understand how those sorts of attacks work, and then hopefully be able to generalize that kind of thing to other similar structures. But the homeworks that we do on heap are going to look at attacking the program and not the heap structure. It's a lot more reliable, and in many cases, it's the only way to actually get the job done. A big problem that I see in academic hacking in general is that you can spend a lot of time proving that it's possible to do a certain thing in a certain circumstance, only to recognize that the way normal humans write normal programs for other humans to actually use doesn't set you up in those situations very often. And so you're better off coming at these attacks from an understanding of how programs are actually structured than what is possible in very specific contexts, right? So like, yeah, you could prove you can do these things in this very contrived situation. How often does that come up? Almost never, right? So there's a lot of barking up the wrong tree. All right, so let's talk ASLR. ASLR is probably the most expensive mitigation that exists widely in modern computing. There are newer optimizations, or I'm sorry, newer mitigations that exist in some spaces. This one's the one that really pushed exploitation out of the realm of hobbyists and into the realm of professionals, right? If you don't have 8 hours a day, 40 hours a week to sit and work a problem, this is the one that's going to stop you from getting a solution, right? So when I think about mitigations, I am thinking in terms of the cost. So has anyone ever heard the term, like when buying a car, the total cost of ownership? Right, like you could buy the sports car, the old Porsche, for $10,000, but you're 18, and so the insurance is going to cost you $20,000 a year, and also it breaks down every month, and it costs you $500 in repairs and a boxer engine, and so the actual total cost of ownership is enormous when the purchase cost is $10,000. We use that kind of same idea, total cost of ownership with a zero, or total cost of ownership with a P, if you like. That was a term popularized by my old boss and the Tau guy, Dave Itel. And ASLR and DEP together are the thing that significantly increased this cost. So in the last lab and in your current homework, you are looking at ROP. And ROP defeats DEP on its own in a fairly boilerplate fashion, right? Once you figure out how to build a ROP chain, it's not that complicated. When you do the homework, you'll see if you figure out how to build a ROP chain for one program, apart from the pivot, it's going to be the same, right? You're going to have the same pieces. You're always going to need the pop EAX. It's always going to be the same bytes. It's always going to be in the same order. You just need to know what the addresses are, right? This stops you from knowing what the addresses are, right? And so by itself, DEP is almost nothing. For a very long time, after DEP was introduced, it was basically a nothing for attackers because you were always guaranteed to have at least one library that had not been compiled position independent, right? When I compile your homework assignments, if you look at those make files, there's a PIE flag, right? Position independent executable. And what that means is that it can be loaded to an arbitrary address instead of being loaded to a known static address, right? And because every single third-party vendor and every single operating system had not recompiled every single library, it did not matter that some hardware had DEP support. You would just use one of the libraries that didn't move, and there was always one, and it was always plenty, right? It is somewhat counterintuitive that you will always have the gadgets you need, but for any sufficiently complicated program that does anything anyone would want to run, you will always have the gadgets you need. The gadgets you need are very simple. They're always there. It's very common. But when you combine that with ASLR, not knowing the address of those gadgets, it's a much more significant problem. And it's a more significant problem for a couple reasons. The first is very often you will need multiple bugs, multiple primitives, let's say, in order to get around ASLR. Previously, you needed a primitive that allowed you control of EIP. That's all. And you were done, right? Now you need a primitive that gets you control of EIP or gets you control of ESP. And then also you need a primitive that will allow you to get back some data about the program. Okay. Now, the primitives that allow you to get back data about the program are a little bit more limited, right? We are talking, you're going to need a side effect of something the program does that's repeatable without crashing the program, that can make changes to the program such that it gives you an output of something you can use. And you have to be able to interact with that program in such a way that it'll say something back to you, right? And there are a lot of situations where that may or may not be the case. And in some cases, getting around ASLR is a seriously significant problem. So somebody had posted a post about how KASLR on Windows is totally useless. Right? Is that you?
I think that was me.
Yeah.
I was like, I found a good post. And you're
Yeah.
like, it's horrible.
Here's why it's horrible. For locals, beating ASLR is easy. Windows kernel leaks pointers to you as a matter of course. So you can always beat it locally, which is why I'm bad at finding peaks or building peaks, because I was a Windows kernel person for a long time. Remotely, it's very hard to get around KASLR. And at the time that they introduced it, Windows kernel remotes were rampant. I just had a conversation about state machines in funny places with Sam, who is a, I guess, semi-local famous computer nerd. And everyone said hi to him as he walked by. And the canonical one was fonts, right? So the font interpreter on a computer is a state machine. It is Turing complete. It's a programming language unto itself that draws things on the screen. That lives in the kernel, right? There were a lot of bugs in there, and you basically can do arbitrary code execution in the kernel by drawing font pictures, right? With ASLR though, that font would have to communicate back out to you some information about where things are in the kernel, and then you would have to be able to continuously interact with it. Now, think about the bugs that you've seen so far, right? You can cause that program to crash. You can get control of that program. But can you make it do something different without crashing and still continuing to execute? And the answer is, in all the situations we've seen, because they're contrived, they're not complicated programs, no. Right? So you would not be able to beat ASLR on those programs. You just wouldn't be able to. Right? Luckily, nobody writes toy programs in the real world. That's not why people write programs. They write very complicated programs that do complicated things, and they go back and forth interacting with humans and other computers. And so very often, you can beat ASLR, but that's based on how complicated the program is, right? So what does it actually do? We are going to focus on good implementations, and when I say good implementations, I mean someone writing the operating system has not done a boneheaded thing that allows you to walk around them. That's not always the case. There are times where someone makes an implementation of ASLR that's not very good, which means that will be an example of a not very good one. DLLs are loaded in the same order. So I randomize the first one, but since they're all loaded in the same order, I always know this one is going to be 2 away from this one, and I know the size of them, so I can still do math, like relative math, right? A good implementation would be all 3 of the modules are in random places, right? We're going to assume good implementation, and if you are a good hacker, you will always do that. If you are relying on people making mistakes in their implementation, your bug will not be portable. There will be situations that you cannot succeed in. And if you go on in this space and you see mitigations added, what you will see is your peers fall away, right? When there was no def in ASLR, everybody was a hacker. And then when we moved to the heap, only 20% of those people were still hackers. And the other 80% had to go off and get a job doing something else, okay? So if you don't rely on bad implementations to solve your problems, you will be prepared for when there are no bad implementations left. If you do rely on them, you're going to have to find a new job in a couple years. So we'll only look at good implementations. So what happens in a good implementation? Let's actually take a look. And I will post these files for you for later. All right, so this is a dumb program that just is going to let us print out the addresses of different places in the program. I'm going to print out the BSS.data, the GOT, stack, the heap, and we'll see what happens as we load this thing over and over again. One more thing I want to show you. This one does not have the no PIE flag, so this is going to get randomized. All right, so let's run this 3 times and then take a look at the differences here. Okay, so first thing to notice, .bss, .data, and .got on all 3 of these runs have the same high order bytes, right? So when I say high order, I'm saying look at these big 2. Okay, this guy here, 58EA, 58EA, 58EA. This guy here, 653E, 653E, 653E. Okay, so these, which are part of the loadable module, so either the shared object.so or the executable binary itself, they're all loaded together. They are not in separate places, right? So even though they're different sections in the binary, they're loaded, they're only randomized together, okay? So when you load a module like that, all of the data that gets loaded as one chunk. It's always going to be in the same place relative to one another. If we look at the low order bytes here, even as they change, 12EO, 1280, 1230, 2EO, 280, 230, 2EO, 280, 230, right? So it is only at the page boundary that things are randomized, okay? Does that make sense? Right? And so what that means is, relative to the start of this module, the GOT is always the same distance from the start. So if I know the address of something in the global offset table, or if I know the address of something in .data, like I know the address of a string, through subtraction, I can find the base address of the module. Does that make sense? Right? And that means it doesn't matter what pointer I peek out of this module, it will always tell me what the base address is if I know the version of the library. Right? If I have a copy of it, no problem. So if you are looking at remote bugs, what you will see is such and such a DLL version 6.0, here's a set of offsets in it. Right? This is the offset in this version of the library for POPI-AX. This is the offset in this version of the library for POPI-BX. When you write your code, you will probably have a table that looks like that. You'll have like base address, I give it here, and then here are all my offsets for every gadget, right? You don't have to put in the whole address. That's what Jade did in hers as well, right? It was a base address, and then you added an offset in each of those. So if my remote exploit has been written to target 3 or 4 different versions of a program, I'll have 3 or 4 different tables of statically coded offsets. And that just says the string that I leak is this far from the beginning, and then the gadgets are this far from the beginning, and I do the subtraction with my peek, right? Second thing to note, in all of these, the stack and heap are in different places, and they are not adjacent to these guys, right? So yeah, 5e is the same, but DD is not. 5b is not 5a, right? So your stack and your heap are going to be in their own places relative to some base number that the operating system chooses, okay? Because they're not part of the module, right? That space that is not initialized at the start of the program, there's no known data that gets put there at the beginning of the program, right? The loader doesn't know anything about what's going to go in there. When the program runs, it's going to dictate what goes in there, right? So these guys are loaded separately, okay?
When I do like info proc mapping and it shows me like the region that's set aside for the stack, will that always be the same? Like obviously where the stack like starts depends on like where the relevant stuff starts, depends on like environment variables, what's pushing it down. But if ASLR is enabled, will the stack always be in that same position at the end of?
No.
Okay.
FFF3, FFA4, FFPC, right? So they're all different. Your stack frame, and the reason you can draw the stack reliably is because the stack frames are always the same.
Right.
Right? But where the stack is loaded relative to the rest of it, always going to be different.
Does the stack always start with FF?
No.
Okay.
It
It's
is,
just coincidence then.
so it is by operating system that there are conventions. In the older versions of Linux, it was always BFFF. On Windows, it'll be in a different place. On OS X, it's in a different place. Different kernels will put it in a different place. But it tends to start in a similar spot. Do you have a question?
So are you saying that the stack, the order of the pages will stay the same, right? Like the stack's always going to be the last page that gets mapped?
Probably, but there's nothing that says that you couldn't write a loader that did it differently, right? Because there's nothing in the operating system that says that, right? So other thing to note here, specifically with ASLR, and then when we talk about heaps, I want you to learn the problems the operating system is solving and how they went about solving it in this specific case. But what you should not learn is specific details of specific implementations, right? What you should go in looking at a problem is, okay, I know the problems they need to solve. I know the 3 ways that the computer is best able to solve that problem. how did they specifically write their implementation? But the implementation will always change. This is another place people fall off of hacking pretty hard, is they learn specific solutions to specific problems, right? Like, how do I own this thing? Oh, I overwrite ret. If you know that, you're good for a certain amount of time, and then you'll never be able to hack it, right? What you need to know is, this is how the problem is generally solved. Here are some ways people have solved it in the past. I can recognize what they're doing, but I need to know what specifically this program in this context is doing. I need to be flexible enough to understand that, right? The problems they're solving will always be the same. How they solve it is going to differ. Okay, but the important thing to notice here is that when you load a module, the whole thing is loaded as a chunk, and you can do subtraction to figure out what you leaked, how it relates to the base. Okay? So then the question is how does it still work? When we look at the programs in our homework, there are a lot of hard-coded addresses, right? When you load a string, that string's a global. Generally, it's moving a 4-byte value, an absolute string pointer, right? It's not relative. Sometimes you're going to call externally to other libraries, right? How does that work? So the answer to how the function calls work is they rely on that PLT. So that PLT lives in the module that calls the external function, and it is a fixed offset from the place that it's called, right? The compiler knows what address it's writing bytes to relative to the start of the thing it's outputting, and it'll say, oh, here I'm 2048 bytes away from the PLT. So I'll add where I'm at plus that. Now I know where the PLT is, right? When you make the call, it's going to be at a different address every time, right? If you call twice. But the compiler knows, it's building this thing, it knows the relatives offsets from where it is, right? So everything's done relatively. So how do we get globals in our own space? How do we get a pointer to the thing that printf is printing out, right? People have had trouble getting flag.exe pointers in their Roth code. And the answer is, there's a function call that looks something like this. And so we are looking at our architecture. This is a get PC thunk. A thunk is a small chunk of code that does something very specific, generally in assembly, that is inlined into code. This is a get PC thunk, which is get the program counter. It's another way of saying the instruction pointer. So if you look at MIPS or ARM, your instruction pointer will be referred to as a program counter. So this is a generic way of referring to that. And then this one is BX. So we're going to put that value into EBX or RBX, right? So what is that actually going to do? Let's take a look. All right, so here is a set of code that is going to get us a global value, and it's going to push it as the argument to printf, right? So the first thing it does is it's going to call that get thunk, and the get thunk is actually going to do this. Let's look at it together before we go on. Yeah. So it's basically doing what your shellcode is doing. It's going to say, when we did a call, what was pushed onto the stack? I've asked this question 3 times in every class. Somebody help me.
Next address.
The address of the next instruction gets pushed onto the stack. This is going to give us the next thing on the stack, right? So it just moves that return address into EBX and then returns to it. Okay? It's basically the same thing you've been doing in your shellcode. It says, where am I executing right now? Give it to me.
That solves my issue.
Okay? So now that EBX stores where we are, the compiler says, here I know where I am is 2077 bytes away from the thing I want. Okay, so I add that there together, and now I have the pointer to my segment. Right, so this is our pointer to the segment that a string is in. That's going to be in our RO data. So there's our RO data, and then it knows, okay, from the start of RO data, B0 in is going to give me my pointer, so load effective address to get that pointer. Good to go. Now we've got a global pointer. Okay, that happens all over the place in code that is PIE. So if you want to know if something is compiled position independent, you're going to be looking for this thunk. Okay.
How do we know that it's like 2077 away from like the table?
The compiler knows.
Okay.
Right? Because the compiler built the code, so it knows, and it puts that in there for you. How do you know? You know because the compiler knows, and the compiler wrote the code, and the code works. So you look at the code, it tells it. Does that make sense?
Yeah.
Okay. Yeah, I'm not trying to be like cheeky. That's just, the compiler knows it built the code. It's the same way when you run NASM and you give it a symbol. Like, it just does the math.
Yeah, okay.
Right. Compilers know the distance. We can know also by looking at what the compiler knows. All right. So we've looked at what a good implementation of ASLR does and kind of why it does it and how it makes your life tough. Joy's not here. Joyce has been asking me all week how to bypass ASLR. You're going to have to take notes. So we're going to introduce a type of primitive here, which is called a peak. This is, if you use the word peak, you will be giving away your lineage as a hacker. The term peak is used specifically by contractors of certain contractor companies for the US government. I first heard it from Mantech contractors, and the reason I use the term is because it is specific, right? There are many ways that people use the term leak in computer science and specifically in hacking. If I say a memory leak, what that means is you have asked the allocator for a pointer, and then you have lost the pointer, and there's no way to free it back to the operating system. So if your program runs over time, the memory footprint will grow, and it will never shrink again. That's a memory leak. An info leak is the program told me something that the program shouldn't let me know. Squinty face. Right, so an example of that would be you info leaked the crypto key in Jade's program. That's an info leak, right? If I'm doing like a Heartbleed style attack where I'm looking at how long it takes an algorithm to run to figure out something about the data, that's an info leak. That's a timing-based info leak, right? This is a specific type of info leak, and it is the address of something at a known offset in a binary module. Okay? It is a pointer. A peak is an info leak that lets us know where something is in memory is loaded, specifically so that we can perform ROP. Right? There are other ways to use peaks besides ROP. In this case, let's make it specific. Okay? Which means we're leaking something from the module itself, the binary module. So the text segment, the data segment, the BSS segment, the RO data, which are all at a relative fixed location from the base, as we have shown previously. Okay? So, what can we peek? There are a number of useful things for us to peek. These are the common ones. Okay? vtable addresses, return pointers, right? Return pointers are pointers to code pages. Any static global string, so a string in memory, an address of that would be just fine because that's going to be in a module. It'll be in data, RO data, or VSS. Or JIT page addresses. So JIT page addresses are useful because they are executable, right? And we can understand or guess what data will be there. So if we want to get super generic about this, anything that you can peek is useful if it lets you know the address, a base address of a module that has executable pages, or is an address of an executable page with data you can control or guess. Does that make sense? Why all those things become useful to us in this situation? Yeah, okay. I want to do a quick V-table digression for undergrads and again for grad students. In object-oriented code, you can overload functions, right? Has everybody overloaded a function in object-oriented code before? Understands kind of how that works? Has everybody done like multiple inheritance in object-oriented code, right? And the way that works is I can create an object and I can call it in one of two different ways, either as the parent or the child, right? And on the fly, your program has to be able to figure that out. I could make an array of vectors, and the vectors, even though they're a vector type, can store a different type of data inside the vector, right? But I can still iterate over that and call a print function, right? But that print function is different per type, which means that when the compiler writes the code, it doesn't know what function will ultimately be called on that call. It's got to figure it out at runtime, right? Here's how it does that. This is the way that all of that is handled in native code, and everything that is not interpreted as it goes, run through a virtual machine, will be implemented in this way. You have a class, and the class lives on the heap. It is dynamically allocated with either malloc or new, right? You can have an arbitrary number of those based on the input of the program. And it's got a bunch of stuff in it. It's a struct at its base level with member variables. But it also has functions aligned to it, right? There's a list of functions that come in a class or any object-oriented structure. The way that is implemented is there is a vtable pointer. That points into a module, probably a .text page, and it's got a list of function pointers. If it has inheritance, there will be multiple vtables, first the parent and then the child. And based on how it's called, it'll pick one or two. This one goes to a different vtable, also in a text segment. So this is readable, not writable, executable. This is read-write, not executable. Call this the parent. This is the child. Okay. These point at, so it's probably going to be in .data. Probably in RO data, I would guess. That's where I would put it if I were a compiler. And then over here, you've got readable, not writable, executable assembly. Asm. Okay? That is how vtables are implemented. That's how inheritance is done. That's how function overloads are done. Okay? This is just a structure that lives in memory. And if you have a heap overflow, or you have a use after free, or some other memory corruption on the heap, you may be able to control all of this. Okay? Which means you will have an indirect pointer to code that gets run. I would say something like move EAX class pointer, move EAX 0x plus C, I want to call the third one. I'm sorry, 8, 0, 4, 8. So 8. Call the AX. That is what it looks like to call a virtual function table pointer, right? Pointer from the class, pointer from the vtable, call the pointer, okay? Because these things are sitting on the heap next to other stuff you can control, they are eminently leakable, and they will tell you the address of the module, because that's where the vtable lives. So in addition to being something that you can overwrite to gain control, they are something that you could leak to know where a module is loaded, okay? Return pointers, fairly obvious, right? They're on the stack. If you can get it to print it out, there are a couple ways you could get it to print it out. I'll talk about that in a second.
So is this work with like a C program?
Every C++ program will be like that. C programs.
Because C is not function oriented.
Exactly. However, if you as a programmer wanted to have a dynamic structure where you could change how that structure acts in certain situations, that would be how you would program it yourself. And I've seen a lot of C programs where people do that. I've written C programs that rely on kind of dynamic function calls, right? And that's the structure you would use, right? So the compiler won't do that, but a C programmer who is clever and trying to implement something like that would.
Can you just explain again how this works with like overloading, like how it relates with that?
Yeah, so here's my base type function, right? If I overload, what I'm doing is I'm adding another vtable, right?
Yeah.
Sitting underneath it. Right? And so then how you call it will determine whether the overload is used or not, right? So that's how it'll work. Yeah, your overloading is yet again its own vtable pointer. Because I still have to be able to call it as the parent. If I couldn't, it would mean it didn't have a parent implementation, right? Yeah, so it wouldn't make sense to overload, you just be adding, right? So anytime you've got like an equals, that's going to be like your constructor, and it's going to have, it has to have one, right? So even if it's undefined, it still has to have a constructor. Yeah, so then any static global string, so anytime somebody is printing something out, or say there's a header to a network packet that's somewhat standard for the type of packet that's being sent out, that's going to be static data. That's another thing you could leak. Excellent. And then JIT page addresses are somewhat obvious, right? If you can leak that, it's not in a module, but if I know what's going to be there, and if I am doing something that's JITted, I generally sent the script. I know what the jitter looks like. I can predict how what I sent will be there. And so a technique you might use if you were trying to own a web browser would be that you would send JavaScript that would cause the jitter to output bytes that you could use as gadgets, right? Man, I should have switched slides a second ago. This is my problem with slides. I just get off on my tangent and I thought I'd put it there, right? People who did their grad homework and did not see vtables, it's for a number of reasons. One, if you put it on the stack, you're not going to have that. If you didn't have inheritance, it may not show it. It's based on the compiler. In Linux, it will not provide you a vtable if you didn't have inheritance. On Windows, the CL compiler will. So it's compiler specific, right? All right, so the reason we're not going to do peaks in class is because, like I said, they're very context dependent, which means if the program is not complex enough to be returning data back to you, for you to come up with a primitive that is reusable, that means I can call this thing and get it to do something untoward to the program without the program necessarily crashing, then I'm kind of out of luck, right? Because every time I run this program again, it's going to get rebased. Everything's going to get randomized again. When I showed you running ASLR, I ran it 3 times in a row. I didn't reboot the computer. I didn't change the program. It randomized itself. So if you get a peek back, but you crash the program, it's not going to do you any good, right? That's a somewhat more complicated primitive than the situations we've been dealing with now, okay? It's going to be dependent on what does the program do. Like, what are the circumstances under which the program communicates back to you? How complex is what it is communicating back to you? And then how do my primitives interact with that, right? And then if the program is going to be in a state that I can recover from when I use this primitive. So if you have a program that has a global exception handler, has anybody here ever written a try except block where the except block is a star? Does everybody know what I'm talking about? Have you ever done that? Because okay, so when you do try except in a language that has exception handling, when an error occurs, it will check the exception block for what type of errors are acceptable to collect and handle. And what most people will do is they'll just put a wildcard in there. So if anything happens here, if I say I'm writing a Python program and I'm iterating over a map key and there is no entry in the map for that key, my exception handler will handle that and it'll just exit out, right? If I put a wildcard there and I tank the program in some terrible way, like a bad pointer read, that exception handler is going to catch it and it'll just pull you out of the block and the program will go on normally. If you don't understand why an error is occurring and you put it inside a try except block, which is something every single programmer will do, every programmer that writes LLM code will do it all day long because it's going to have error conditions it doesn't check based on your data set. And this is a way for you to hand in that thing that works to your boss and then go home, right? That's a great situation for a hacker because that means you can just screw the program up over and over and over and over again, and it'll keep running, and those addresses will never change, right? So that is gold if you see exception blocks that are a wildcard, right?
So this probably makes languages without typed errors very nice.
Yep. Yeah. It's not so much the typedness, it is the understanding of the programmer. And some of those make it easier for you to not understand.
Right. Well, like with JavaScript and Go, where your errors are kind of just strings, you'd have to then go through and do like a string includes.
It's beautiful.
Which no one does.
It's beautiful. Yeah. JavaScript is terrible, but great.
I don't exactly get why that would be bad, because if you're catching all of the errors, wouldn't that make it so that they're not
good for us, bad for them?
No, I know. No, I'm saying I don't get why it's good for us. Like, isn't it catching the errors then if you're catching everything?
So here's the thing. If you hack something properly, no error occurs, right? So it doesn't catch when you hacked it. It catches when you cause it to fail, right? And anytime somebody catches a failure and doesn't handle it, that means the program is allowed to continue on in an undefined state. And programs that continue in undefined states cause side effects. And a side effect is a primitive you can use to modify how the program reacts, right? The safest program, upon catching an error, will exit. It won't call ret, it won't call its destructor, it will kill itself, right? Anytime that it does something else after it finds out that it's screwed up, that's great. That's super good for you. Okay, but you have to be able to interact with the program. You have to be able to make the program do something that it will call back out again. The hardest thing that I had to deal with in this case is a program that I'll probably talk about at some point later on as an example case, which is the stage fright bug, which is you could send a video file to an Android phone and it would automatically parse it and there was a bug in there. So you could text a video to someone and own their phone every time. Beating ASLR on that is tough though. However, the geniuses who made MP4 made it so that you could put a frame in the video with a URL, and when it gets to that frame, it'll call out to a website. Great, thank you. Now you've sent me my pointers that I need, right? Perfect. As long as I don't crash it when I'm doing that, now I send you a second video. That second video uses that thing to actually get me what I want. Okay. When some program returns something back to you, or it calls out, it interacts in some way, your job is to make use of a reusable primitive in order to change what's being sent back. Okay? Once again, that program not crashing after I've made it do something weird is great because I kind of need 2 chances to get this peak to work, right? The bugs you've looked at so far, the primitives will crash the program if you don't get control instantaneously, right? But that's not necessarily the case with every bug, and clever use of a bug may allow you to return back to something that changes the program slightly, but keeps it running, so you have a second chance at it, right? And you are relying on that. The more complicated the program is, the more useful it is to the user, the more chances you have to do this. Real programs do a lot of stuff. If they don't, people don't use them, right? Especially ones that connect to the internet. Programs that connect to the internet do a lot of great stuff, like that MP4 thing, right? At a first glance, if you're not seriously digging in and doing your research and saying, okay, what are all of the frame types an MP4 player will support? Okay, I have to go and get the specification for that. I'm going to read that whole specification and say, is there anything stupid in here? Oh, thank God they put something stupid in there. I'm golden, right? But if you just looked at it, you'd say there's no way that I could get a peek out of this. It's not doable. And many people will do that. Never underestimate the stupidity of stressed out coders and their bosses. Because there is an office room somewhere with 10 idiots in it that are looking at market data, and they're going to force even the smartest programmers to put the dumbest thing in a program. Because it's going to get them 15 cents per usage, right? Promise you. They're going to do your job for you. Okay. Easy way to do this. The easiest way is you have a situation with an overflow, and it can be on anything. Like RxC, threat, EBP, dumbest possible thing, ABO1. You've seen it a billion times now. This is what the stack looks like. Let me make a simple change to that so that there's actually a little bit of interaction, because there isn't in the normal program. Okay, so all I've done is add a printf that prints out what buff sends, and I've made a slight change so that I'm using stir and copy and not stir copy. Okay. Problem with stir and copy, if you give it the full number of bytes, it has no space to null terminate. So you will put in a string that's not null terminated. Okay. So if I walk up and I write 256, 100, and then I write another 4, and then I stop right here. So I write 104. When it prints out, Okay. Oh, yeah, I don't. All right, so what you see there is EVP, the return address at F7, D9. argc is 2 in this case. argv is another stack pointer. That's the environment pointer, right? So that's what we're looking at the stack now at the start. And I continue here. What you see is I ended up getting a bunch of garbage after my A's, right? Let's run that one more time, and I'm going to do it like this. Is this going to work? Ouch. Yeah, okay. So here's our return pointer is right here. Keep that in mind. Okay. We are now getting F7. 1, 2, 3, 4. Which is on our code page, right? So we're just walking directly up to the edge there, and we're getting a pointer back off that stack, okay? So that method is very, very powerful if you have any type of overflow, right? Especially if it is a heap overflow. I mean, stack overflow, I just showed you, obvious. If it's a heap overflow, you walk right up to the next vtable pointer for the next object on the heap. You get it printed out, okay? No problem. Any type of stack misalignment is gold, okay? And stack misalignment can come about in a number of ways. So in a generalized type confusion situation, which is where the program expects one class and you have provided it a different class, right? You can build that situation with a use after free very easily. In that case, if you know what functions that class allows you to call, you can call one that will interact outward. And what it will do is it will assume that the things that are on the stack or the things that are on the registers are arguments to one function, when in reality you will be calling a different function. If the different function treats the things on the stack or in those registers as pointers of a certain type, and they're not, you may be able to get back out something else. So what's a good example of this? An example of this would be any sort of print function, stupidest possible solution here. A print function that expects to take 3 arguments and print them out. You only give it 1 argument. It's going to take the next 2 things off the stack and assume that they are printable and print them out, right? And if the next 2 things on the stack are pointers to something you can use, you're going to get those pointers, right? So this is the way that a lot of modern peaks are created, okay? You perform stack misalignment by calling a function that expects a certain number of arguments when you have only pushed a different number, right? Either greater or lesser, okay? Questions about that? I know that was kind of vague and hand-wavy, but I think the printf example makes a good one, right? You can turn things into format string style vulnerabilities, right? If you can provide the first data input to a function and you can force it to call printf or some format string function, well, the thing that I would provide it would be %x, 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 and it's just going to walk up the stack, pulling the next thing off there and printing it as a hex number, right? That would be golden for you, right? You would just print the whole stack out. You could just use the bug as a debugger to read the stack. Okay. I usually don't show the format string bugs because compilers will find top-level format string bugs every time now and throw an error. However, you can use AO primitives to turn something into a format string bug, in which case it would be very useful, right? Kind of a second order move. Just like in the very first thing you did, you turned a overflow into a write what where. That stuff, those opportunities are everywhere in exploitation, and it will be incumbent upon you to think in that way. How do I stepwise turn something I have into 5 different other more useful things, or 5 different things that allow me to solve different problems? Okay. Here is an extremely fun one. How many people have written a hash map implementation of their own?
I think we all had to in 187.
Yeah.
And how come everyone else isn't raising their hand?
Forgot.
LLMs had just ChatGPT had just launched, so it's possible. The history. Yeah. It launched in November.
That was second semester.
Yeah, no, it was second semester. You used the Zybook.
Remember what you cheated on for future reference. If you're gonna cheat, this is the problem with cheating and lying. When you cheat and lie, you need to keep a secondary state in your head of the diffs. So that depending on who you're talking to, you can apply the diffs or not.
Yeah.
Okay, it gets very heavy over time to cheat. You want to do it in contexts where there's no crossover. Okay. Well, a very common thing people will do is to use the pointer as a random number to build their map, right? Or use it as a random number in their algorithm in general. The pointer is always different. Therefore, I can use it as 1, a unique identifier for an object, and 2, a random number that will never overlap with another thing, right? If someone does that, and you can add things to the hash, then you can figure out what the pointers are. If someone does that and you can't add things, but you know what's in the map, you can figure out what the pointers are, right? You just have to reverse the math, but it's always possible. And depending on how they built those algorithms, you're good to go. This is the method by which a lot of people beat iOS ASLR, the iPhone, because Objective-C does this all over the place, and there's no way to fix it. The whole thing is built on it, right? Everything's built as a hash map. All the hash maps are using the pointers as random values. Peek it right out. Okay. There are a lot of, if you are a mathematician, clever ways to back people's random number usage out into peaks. Okay. I've had situations where we spent like 4 months trying to figure out how to peek something out, and then some Sam character came over to the office, and we were like, Sam character, can you help us with this situation? And they were like, oh yeah, you just use the Chinese remainder theorem and you can back this thing out. And we were like, cool, thank you. Let me go look that up. And then we did, and it worked fine. And then the thing was done, right? So people will cheat in ways that they don't understand can be used against them constantly. And your creativity and your understanding of these concepts will let you beat them, right? And there's no way for any automated solution to figure out all of the possible ways that this can be done, so it cannot be fixed in an automated fashion. I am not clever enough to know how to use the Chinese remainder theorem a priori to stop someone from peeking my pointers out, right? And there are a lot of programmers worse than me. And they're all going to do this stuff all over the place, right? Last one. We got 10 minutes left. Last one is going to be partial overwrites. We did an example in class. I didn't hand you this example out, but I think it's in Canvas. And it was based on another Joyce question, who's not here today. And the answer was that, yes, a single null byte overwriting the low order byte of EBP allowed you to get control, right? You didn't care what the absolute pointer for EBP was because you weren't overwriting all of EBP. You're only overwriting the low order. So you were just changing where it was relative to itself, right? Because the stack frames are always the same size, the number you were subtracting was going to be the same every time you ran the program. It was always going to work. But you didn't need to know where things were loaded because you weren't changing the whole pointer, you were changing part of the pointer. You can take your write what where and misalign it. Even if you have a 4-byte write what where, you could overwrite the high order 2 bytes of the thing immediately before and the low order 2 bytes of the thing immediately after and get yourself a partial overwrite, right? And so then instead of saying, I need to know globally where everything is, I don't. I need to know where it is relative to something else that's useful to me, right? That sort of eliminates the need for you to it's generally not going to give you the ability to write full rock chains. So you would use this to turn a write what where into a peak, not knowing anything about your full address for your write what where, right? But it allows you to take a write what where that generally requires full knowledge of a pointer and not require you to know full knowledge of the pointer and change it into something else. If you are lucky enough to have a single gadget that can solve your problem, and in a lot of the cases there is a single gadget that can solve your problem if you are clever and know what to look for, then you could just get that one straight up. And as long as the thing doesn't crash, you're still good to go, right? The example that I gave you for the homework is a case where if it were in a loop running over and over again, a single gadget would let you peek with that, right? Because it's a function pointer call and it just returns back and it doesn't necessarily require you to trash anything, so there's nothing to fix. That would be a case where you could do something like that, okay? Does that situation make sense to people and let you kind of understand how you would make use of something that seems restricted in a slightly more clever way? Yeah. All right. Another note here. On 64-bit platforms, ASLR is generally bulletproof, and you should assume it is. If you are working in embedded platforms, 32-bit processors only can address in a virtual memory space how much memory? 4 gigabytes, right? FF is 4 gigabytes, right? And that means you can perform some obnoxious tricks, especially if you don't care how slow the program gets. You can cause unlimited object growth in certain situations. So let's say you're looking at a 32-bit web browser, and you can send JavaScript to the thing. You can allocate an arbitrary amount of memory. You can control what goes in that memory. I can say, oh, well, I know that the way that the allocator works, and this is an implementation, a bad ASLR implementation that's required for 32-bit, the kernel takes up this much space. The modules in this program are going to take up this much space. I know that stupid allocator puts its heap at FF every single time, or FF something. If I force it to allocate 2 gigs, I will definitely have control of this range of addresses, right? And there are a lot of situations more restrictive than that. You can still pull that trick off. So embedded systems, ASLR is not nearly as big a deal just because of the amount of memory that it will address, right? Yeah, I think that's all we got for today. We're 5 minutes from done. We're going to have a fun grad student seminar after this. So all the grad student wannabes, please stick around.
The PC function that can't get moved around, right? Like that has to be in a well-known location inside the.
No, it has to be in the module itself.
Right. Okay. Because that can be a relative.
That's why it's a function, because it's three lines.
Yep, that makes sense. Yeah. I'm able to go into an MBAC and get myself to read my experiment just to get it. Using this but that writes out the equation of EAX. And I can't find any way to get it from EAX. That way I can pass it.
You can use it in another place.
That way I can pass it into like the right as well.
I like reading
So yeah, I like mainly because I'm
doing the guy to like gadgets.
I don't have
I haven't worked with that. I have but like, I'll target with you.
Point it. Point it.
Okay.
And you can put that in your neurosis.
I was looking at it right now.
There's like the pump pop that was for like EDI and CSR. I just wasn't able to find a way that I thought would let me get data from PAX.
The computer figures out how to make it run. Even the right error.
I don't know if MMAP is the solution. I think there is, but so if you just like M protect it, you're just ready to have it.
For number 4, yeah. Could you reduce 4 bar to ATM or 4 to ATM? Well, I'm saying for it's TR or either TR nor OTR, so you go to both here. Oh, very targeted.
So document one keyboard.
Right, so all grad students who are going to stick around,
I don't want to both.
Yeah.
please come to the front of the room. So I can read you your algorithm.
Could you do it by reducing it to 4 bar to ATM bar, Well, you were first, for the first time, I would my bad. So I would ATM 2 4, right? And then I can reduce ATM 4 bar or ATM bar 4 ATM 4 bar. Because if 4 bar is not ODR, then Andres only so which one did yeah, I'm trying to think about how we like the
Oh, there was an exercise. That's why I wasn't like actually trying to call you out. No, you had to really cry.
and then my mom walks in. She's like, okay, why is it like that? Why don't
I tried to bring it. No, I haven't gotten the code yet. Mr. Powell, what are you up to? The CTI. I'll work on it. Oh, yeah.
You have to say, if anyone.
Yo, when we go camping, Joseph, can't bring Owen camping.
I'm scared Alex will send me a message on this one. I mean, the